Morning. All right. So on Tuesday, we spent quite a bit of time working through and working with the t-table. So just kind of getting to know the t-table. It had some properties that we were familiar with. Degrees of freedom, for example, right? We've seen degrees of freedom for chi-squareds already. And so that's not really something that's unfamiliar. I might feel weird still, but it's not unfamiliar, right? And so let's do a little bit of review. We introduced the t-table. Right. And we also said that for one sample mean, so if I have one sample and it's a means question, right, which means that I'm analyzing numerical data, right, because then I can talk about the mean or the average. And so for one sample mean questions, we said that the degrees of freedom is going to be n minus 1. Right, I've only got one sample size and so my degrees of freedom is going to be n minus 1. Okay. In this course, we don't really talk about, what the degrees of freedom are, and we don't really ever talk about it a ton. It's because you are estimating one thing, so the mean, and then, but it's also, it has to do with how many things you would know in order to know everything about the mean. So it's kind of, I don't want to say complicated, but it's a little bit above our level here. And so, so we just kind of skip it. So I want you to just remember that the degrees of freedom is n minus 1, and then we use that. And we don't really think too much about it, right? But we also have to remember that t's, right, as soon as we've calculated any t, right, and what we're going to see is that there are different ways that we could calculate t's, much like we saw with z-scores, right? There were different ways that we could get a z, right? We could look at one sample proportion, or we could compare two sample proportions, right? So there were different ways to get to z, and there will be different ways to get to a t-test statistic. Okay, and so each of those is going to have some degrees of freedom. Now, it's all kind of numbered weird, but if you go to that formula sheet that I posted as a guide, you'll see, if I can find it, you will see, it used to be chapter 5. So, and we used to talk about sigma known, but we're skipping that because we don't actually need that. It never happens. It's kind of an old school way of introducing things. So we axed this and we moved straight into here. So what I want to grab here for today is this little chunk. Okay, so notice that down here at the bottom, it does have the degrees of freedom. Right, so it shows, and we'll talk more about what's going on in here, right? But it shows us how to set up our hypotheses, and we've seen this type of scenario before, right? With one sample proportion, we want to compare it to some hypothesized proportion. Now we have one sample mean, and we want to compare it to some hypothesized mean, right? So some value, okay? And then we'll calculate a t as part of our test statistic. And then once we have a t, we can use the t-table, right? So you have to use the t-table for a t. And I know that sounds silly when you say it like that, right? If you've calculated a z, you use the z-table. If you've calculated a t, you use the t-table, right? And I know it feels like, well, yeah, of course, what else would I do? But the number of times that I see people kind of mixing and matching, I just want to say it a couple of times. I'll say it again later. But if you've calculated a t, you have to use the t-table. Okay, and the t-table requires that we know the degrees of freedom, which is just going to be n minus 1 in this case. right? And then we've got this confidence interval. So we didn't introduce any of these formulas last day. That's what today is going to be about, right? But we did talk about how do I find a T star, for example, and how do I find p-values using the T table. I know there's so many little P's and T's and Z's and Chi's, and it's crazy. But with practice, you'll be able to keep them all separate. P-values. Just kind of looking ahead. So tomorrow, the video that I'll post is for paired data, right? And so we're going to be in this little area here. And what you'll notice is that nothing really changes from what we introduced today. It's just a specific case of what we're doing today. And then next week, we're going to talk about 2 sample means, and notice how the degrees of freedom is just going to change slightly, right? And so you have everything here. And with this formula sheet, you could figure out how to do the rest of these types of problems, right? The problem is identifying what type of question you have. So that's going to be what we're going to work on mainly. All right, so let's see here. So we talked about the T table, and then for 1 sample means questions, the degrees of freedom is going to be n-1. And so that's kind of, I guess, the end of the review. It was just on Tuesday, so not a lot of time has passed. So let's just jump right into it, okay? If I paste this here, I've clarified the sigma unknown in this case, but for us, you can ignore this if you want to, right? So we can ignore this. Because it's referring to a case where we pretend to know sigma. What is sigma? Sigma is the population standard deviation, right? So if we think about it for a second, if I have the population standard deviation, that means that at some point I have collected the entire population. That doesn't really jive with what we're trying to do, right? We're trying to learn about the population. So how on earth would I pretend to know that I know the population standard deviation? Why wouldn't I just go and figure out the mean as well, right? And so that doesn't really make sense. So for 1 sample mean, we're just going to focus on the t-test. Okay, so the steps for hypothesis testing and the steps for confidence intervals and how we interpret confidence intervals and hypothesis tests stay the same, right? So we're getting comfortable with that still. I know it's probably not 100%. That's okay, right? As long as we keep working at it. But what we have for our hypothesis tests, and I'm kind of glossing over the conditions because what we said was as long as we have a large enough sample size, or if we can assume that the population that we're drawing from, even if we have a small sample size, if it came from an approximately normal distribution, we can go ahead and apply the t-test. Okay, so the t-test is pretty capable of handling these kind of small sample sizes and a little bit of skew and that kind of thing. So pretty robust test statistic. So I'm going to skip the conditions for now. I think I mentioned them last day. But that means it's not going to be an emphasis for you when you're working on questions either. Okay, so let's start with hypothesis testing. For 1 sample mean. Okay. That means that we've been given some sample size, some sample mean, and some sample standard deviation. So we're given n, which is the sample size. we're given X bar, which is the sample mean, right? And so here you only have one of these sample means, right? And that's where the type of question comes from. S is the sample standard deviation. And often you'll be given some alpha level, but not necessarily, right? And so optional is alpha, which is the confidence. It's the confidence level, but it's the opposite of the confidence level. The name is escaping me at this moment. It's not the confidence level. Significance level. Significance level. And if it's not given, the default is 0.05. Right? So there will be a lot of questions where it's not given, and that's okay, right? Then you have a default of 0.05. And just in life, that's going to be your default as well, right? So, so you don't need to be kind of hand-fed a significance level or an alpha level. You know that you can just use 0.05. Okay. So those are all the things that you're given, right? And also, maybe I'll make one more line of room here. You're also going to be given some mu naught, which is going to be some hypothesized value. So some value that you want to compare your sample mean to. All right, so this is the hypothesized value. And I guess I need one more line. Maybe I'll give myself 2 lines here. Bump it up if it's too spacey. Is the hypothesized value. And this is the value we want to compare our sample mean to. Okay, so that's important. That's the same situation as we had for one sample proportion, right? If I just have one sample, then I have nothing really to compare it to, except my research question is going to lead me down the path of, okay, I want to compare my sample proportion to some hypothesized proportion. And now we're talking about means, right? I have some sample mean that I want to compare to some hypothesized mean. Okay, good. So given all this information in the question, right, that's going to help you identify that, okay, I have a one sample mean, right, question. If I have just one sample, and you're given the mean and the standard deviation of that sample, right, then you have a one sample mean question. Okay. So step 1 is to state the hypotheses. And just like we saw on this snippet from the formula sheet, oh, it's just lagging a little bit. Wait, didn't mean to do that. Our null hypothesis is that the mean is equal to this hypothesized value, right? And this is going to be replaced by some value. And then the alternative is that mu is not equal to that value. The default is not equal to. That makes a two-sided test, just like before, right? But we can also test less than or greater than, making it a one-sided test, okay? And so that's the same as before. It's just that now we're hypothesizing about mu, right? We're hypothesizing about mu, which is what? Our population mean, right? So we're hypothesizing about the population, but we have to use the sample information to do that, Okay. So exact same as we had before, our null hypothesis is that mu is equal to some mu naught. And depending on, how comfortable you are, if you're testing a one-sided test, so if your alternative is that mu is less than mu naught, for example, then you could in theory alter the equal sign to be greater than or equal to. But I don't want you to take it that far. I think it's safer if you just always have an equal sign and kind of ignore the other case. But if that makes sense to you, that's great. If not, that's okay. You can just ignore it and just always use the equal sign. But notice how it's either equal to or it's less than, but we're forgetting or ignoring the times that it's greater than. Right, in this case, but the default here is going to be not equal to, so I'm going to change that, right? And so here, the default is a two-sided test. But it can also be less than or greater than, but could be less than or greater than. Yeah. So that makes a one-sided test. And maybe you know what? I'm going to bump this over. It's only because I'm dealing with a page break here, right? So the page breaks here and I'm just trying to keep all this information on the same page, but it's a little bit tricky. Right, so this makes a one-sided test. How is that reflected later? That means that if I have a one-sided test, then I'm going to need a one-sided p-value, right? So in step 3, we find our p-value, and that's when we have to go back here and look at the alternative hypothesis and figure out, okay, do I have a one-sided or a two-sided test, right? And that's going to determine whether I need a one-sided p-value or a two-sided p-value, right? We already saw in the table that it's all laid out, so you just pick whichever one you need, but one is just the other one multiplied by 2, so it's not too bad. You could handle it on your own, but that's this is where it comes from, right? And that's hard to keep track of. Right, you're way down in step 3, finding your p-value. It's hard for our brains to go, oh, I need to go back to step 1 to see what was going on here. Do I have a one-sided or a two-sided test? Okay. But that's what we have to do. And then, so here, the hypothesized value, so this is the null value, which is the value we want to compare our sample mean to. I can't stress that enough, right? I've already said that here. You not. This is the value we want to compare our sample mean to. But I know that this is really hard, right? And so I'm going to say a bunch of stuff over and over and over again, and then hopefully eventually it'll sink in. That's just how it is. Okay. All right. Step 2 is to do the test, which I say generically, right? Doing the test really means calculate the test statistic, but usually that's a little bit intimidating, right? But I think we're ready to start incorporating that terminology. So I think do the test is kind of cool, like do the do, but we're really calculating the test statistic, right? And so here, doing the test means calculate the test statistic, but that's so boring. That's why I call it do the test. It's all about branding, right? And so we're going to calculate the test statistics. So in the past, we've either calculated a Z, right? or a chi-squared, depending on the question. And now, again, depending on the question, we're going to calculate a t, right? So in this case, in a one sample means question, we calculate t, which is x bar minus mu naught divided by s divided by root n. Now notice, right, you're going to want to find the s over root n first and then divide it into x bar minus mu naught. Just as a heads up, right, this is the standard error of x bar, s over root n. Okay. So we take the sample standard deviation and then we divide it by the square root of the sample size, because the standard deviation, right, for our mean, sorry, I just got a direct message, but maybe you could share that in the group chat so that it makes sense to everyone. You want to know the final exam date. I think it's the 19th. Posted it on our Moodle page. Let's see here. That's not you guys. This is you guys. It's down here at the very bottom. Final exam, April 19th from 9 to 12. Feels close. Not that close, but close. Okay. Hopefully that answered it. It says, so just a side note about the final exam. It says that we are in a room, but because we've got this hybrid course that kind of turned online, I guess, it'll be an online exam. Okay, so if you want to, we'll talk more about it as we get closer to the final exam, but don't be scared. It says there's a room, but it'll be online if you can't make it to the in-person, or honestly, if you don't want to be in person for the final exam, that's fine, because I don't really see a point in forcing you to. Just because you're here doesn't mean that you need to sit in front of me and write your final exam. So I'll be kind of gauging what people want to do. If you want to write it in a room with me, that's great. Except we're sharing it with a different class, so it might get like a little bit weird, but so I'm leaning towards just online, but if you want to do it in person, that's totally fine. And we have a room to do that. But I know, confusing. Okay, so the standard error, as I increase my sample size, right, then my standard error is going to get smaller, right? And so, if my standard error is getting smaller, that means my spread is getting smaller, which means my estimates for X bar are getting closer and closer to the population mean, right? And so that's how I take into account the spread. Okay, so the standard error of X bar is just the spread of the mean observations. Okay? And so here, what we're doing up top is we're finding how far is the sample mean from the hypothesized mean. Right? And what we're doing is taking into account the spread of X bar, right? Which is the standard error of X bar. Okay. So we're used to seeing that, right? That's very similar to a Z-score, right? A Z-score tells you how many standard errors. Something is from the hypothesized proportion, for example. And so we're doing the same thing. And so T does the same thing. Okay, so when we calculate the test statistic, right, we just grab all the information that we were given in the question. That's kind of hard identifying this information. But once we've identified it, then we just plug it into the formula and we arrive at some T, right? And so calculate T and round properly, of course. Right, usually the mistakes that I see are rounding errors, right? So you're going to round properly to 3 decimal places, or at least 3. And why 3? That's to match the table, right? So if you have a look at the table, you'll see that in the body of the table, there's a bunch of T's, and all of them have 3 decimal places. So if you keep at least 3 decimal places, if you want to play it safe, you can go for 4, right? But it's to match the table. If you're using software, then usually this is all done in one step where you calculate the T and then it spits out a p-value as well. Okay. So step 3 is find the p-value. Okay. How you're going to structure this is you're going to say using the t-table with degrees of freedom equal to something, right? And then if you end up having to round down, remember you always round down your degrees of freedom. Right, we talked about that and why last day. So you don't want to assume you have a larger sample size than you actually do. So you show how you find your degrees of freedom here. And if you're using something other than that, right, to match the table, then you have to say that. We find that, and what I'm going to do here is I'm going to call this, right, this we can call t-calc, right? Just to show that that's your calculated value. Okay. So then we find that the absolute value of the t calculated, which is equal to some number, we have to take the absolute value, right? If it's positive, it doesn't do anything. If it's negative, it makes it positive, right? And so because of symmetry, it doesn't really matter, but the table only has positive values. So to work with the table, we need to take the absolute value. But notice how we set this up is always going to be the same, right? So it looks like a lot right now, right? But once you do a couple, you'll see, okay, I just put my calculated t and whatever it was here in the blank spot. I take the absolute value and I find the values in the table that wraps around this calculated value. All right. So here, I'm going to fill in these blanks, n-1, and the calculated is from step 2. And this is from the table, and this is from the table. Okay. So then, once we have the values of t that wrap around our calculated t, right, then we've found this range of t's, which we can then translate to the p-values, right? And so from the t-table, we find that t is between these two values, and usually I just kind of link it with a so or therefore or something like that. But again, I center the p-value, and whether I want the one-sided or the two-sided, I tend to show that off here. In this case, this is just a generic one. So the p-value is going to be between two values. So notice how I use the less than, less than, less than, less than. Right? So there's not much to remember here. Right? And I'm going to move them so they're on the same playing field here. Okay. So then my p-value, whether it's one-sided or two-sided, you would specify here, is going to be between two values, right? And so here, this is also from the table and from the table. I want you to remember that you have to read from right to left, because the p-values, as your t's are increasing, so moving out, and remember the curve looks like a normal curve, right? So you can just draw a normal curve, and then you can move your t out further into the tail, right? Moving from 0 out to infinity, it still behaves the same way. Then the area in the tail is getting smaller and smaller and smaller, right? And so we have to read it from right to left. So read from right to left. Otherwise, you're going to have a turned around range for the p-value. Then we're ready for step 4, which is your conclusion. Right? With just a range for the p-value, and of course, if you're using software, it would just give you the p-value, right? And so it exists, but we just need a range, and we can draw our conclusions from that, right? And so the first part of your conclusion is your conclusion, or sorry, compare your p-value, compare the p-value or the range of the p-value, in this case, range of the p-value to the alpha level, right? Is it less than the alpha level or not less than the alpha level? And then, right, once we have a p-value, we know what to do, right? If the p is low, then the null hypothesis must go, right? And so that means you have enough evidence to reject H0. How do we determine if it's low? Well, if it's less than the alpha level, right? So then you're going to compare, your conclusion in terms of H0, right? So if the p-value, or in this case, the range of the p-values, right, it'll either be entirely below 0.05 or whatever alpha level we have, or entirely above. There's never a case where it's going to be wrapped around. So you're safe there. Okay, so you might be on the cusp, right? But it's going to be on the cusp on one of the sides of it. So you're safe. So if the p-value is less than the alpha level, we have enough evidence to reject H0. And of course, the opposite of that is if the p-value is not less than the alpha level, we do not have enough evidence to reject H0. And then I'm going to squeeze it in. This last line here, you don't want to forget, finally state your conclusion in terms of the question, right? So conclusion in terms of the question. Right, you don't want to forget that. Okay. For confidence intervals, they're pretty straightforward, right? We already talked about how we find the critical value. And so I don't really need to go through and remind you of the steps, because it's really just taking that information that we've been given, right? And then we plug it into the formula, right? And then we interpret it the same way that we do with any confidence interval, right? And so I'm starting a fresh page here. So confidence intervals. Is x bar plus minus t star times s over root n. Okay. So this is, again, the standard error of x bar. Right? And the t star is the critical value from the t table. Okay. At whatever confidence level that you are asked to use, and then you find your degrees of freedom, right? And we showed you how, or we talked about how to do that. We're going to do an example in like 2 minutes, maybe less, because I can't think of anything else to say here. But to find your critical value, right, it's the same as finding your Z star, but now you just stop at whatever lines of degrees of freedom you have. Okay. And then X bar is, of course, your sample mean, which is from the question, right? So in the question, you'll have a sample mean, you'll have some confidence level, which you can then use to find your T star. You'll have your S and you'll have your N. So then you'll be able to just plug those in to find your confidence level. Okay. And then you're going to find some lower value up to your upper value. How we interpret, right, this confidence interval is going to stay the same as before, right? So just as a refresher, what's that blurb that we're going to use? We say that we are some percent, usually 95%. So remember we saw last day the connection between 0.05 as our alpha level and the default confidence level of 95%, right? So it's either we're either 95% confident it's within these bounds, or we're 5% okay with being wrong, right? It's kind of the same idea. So we're some percentage confident the interval from blank to blank captures the population mean blank, right? Whatever the question is about. So usually it's 95% as a default, but it's always given. So usually I don't let you do a confidence interval without telling you what confidence level to use. It would be kind of weird of me. Okay. But from the lower to the upper, and captures the population mean because we've built it around the sample mean, right? So now we're trying to capture, and it's really important that you use that terminology, capture, right? I'm trying to capture the population mean. So I use the sample mean, I build a buffer, and now I'm trying to capture the population mean, and then from the question, right? The population mean height, the population mean price, the population mean, I don't know, winnings, I don't know, something, whatever you're talking about, right? But it has to be a numerical variable. Otherwise, we can't take the mean, right? And so here, just to clarify, right, the population mean is mu. So we're trying to capture mu, and that's the most important thing, okay? So, and I know this is really difficult, right? But for confidence intervals, it's so important that you highlight that, okay, the population mean is a value, right? Let's say it's here, but I don't know what it is. I don't have the entire population. I don't know what it is, but we know and understand that our population does have some mean. We just don't know what it is, right? So how I want you to think about the confidence interval is that it's centered on the sample mean, right? And if the sample mean is representative of the sample, then what we're saying is if I take different samples, and it's kind of hard to do here, but if I take different samples, then 95% of those samples are expected to capture the population mean. There are 5% of those samples that might just have a huge sample mean and you're off and not actually capturing the population mean, okay? We don't know if our sample is that sample. That's why we're only 95% confident, right? And so confidence intervals are kind of tricky because there's so many ways that we could misinterpret them, right? And that's why I want you to just stick to this, this prescribed blurb until it clicks and you say, okay, I understand that I'm trying to capture the population mean. Okay. In those kind of notes that I've posted that I'm stealing from, there's only one of the questions that I want to do. I can post the solutions to the other ones. But I want to do the dissolved oxygen level one. And it goes through and it does have it all outlined, but I want to talk about it together. It's my go-to example for this stuff. Where's my page break? There. I guess I'll put it on a fresh page here. No, that's way too much space. Wow. Or maybe, because I have a lot of examples. This is kind of like the most active chapter. It's the one that we tend to focus on because it's what we use in real life. Is usually we're analyzing means. So maybe what I should do, even though I really love this example, the dissolved oxygen level, because it really puts things into perspective. So I encourage you to look at it. I also have shown you how to find it in R, right, which we're not really using because we're kind of short on time, and but we would use it in Stat 240, so it doesn't hurt to show it here. Maybe what I should do is I should just go and show you example 2 instead. The only thing I want to do for example 1 is identify what type of question it is. We know what type of question it is, right? But I want to see, I want you to see a question, and then you'll feel more confident identifying one sample mean questions. Okay, so let's not do example 1, we'll do example 2 together because it's not typed out in the notes that I've posted for you guys. They're kind of, we're loosely following them. I'm mostly using them for examples that are typed up, but all the information that we talk about is in there. So the level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. Sounds important. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. And so here are the results in milligrams per liter, right? So we've got 15 measurements at randomly selected points in the stream. Okay. And we're told that the mean and the standard deviation of this sample is 4.771 and 0.9396. Okay, a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So now we have some value that we say, okay, if it's below this, if it's significantly less than 5, right, then the aquatic life is at risk. Notice that 4.771, it is less than 5, right? What we're asking is if it's significantly less than 5, right? 4.771 is less than 5, but is it significantly less than 5? And how do we decide what is significant? Well, we take the standard error, right? So we have the standard deviation, we have a sample size of 15. And so here, right, I've got one sample. One sample, and the N is 15. And I have one sample mean and the standard deviation, right? So given all this, then I have a one, so the type of question is one sample mean, right? It's a one sample means question. And as soon as we ask, is there evidence of something, it's going to be a hypothesis test, okay? But you could do a confidence interval as well, right? Because you could ask in a similar way, what's the 95% confidence interval? What would that tell you? Well, it would give you a range of values that you're 95% confident might capture the population mean dissolved oxygen level in the stream, right? So, but in a similar way, I'm going to just make a note here. The full worked out solution is in the notes posted on Moodle. Okay. So the one that I want to do together is example 2 because it doesn't have the typed out solutions. So let's go through and do that. Okay. Summit Project is a full-service interactive agency that offers companies a variety of website services. Summit recently redesigned a client company's website and wants to show that sales have increased. That seems like a very reasonable thing to do, right? You want to show that the work that you did significantly increased the sales, right? Before the redesign, the average sales were $24.85, right? So really what we're asking is, have the sales increased significantly from $24.85, $24.85, I guess. After the redesign, an analyst selects 58 sales records at random from the client's 2,000 access logs, and she finds a mean amount spent of $26.05 with a standard deviation of $10.20. Is there evidence the mean sales have increased since the redesign? Okay. So first, what type of question is this? I have one sample, right? I have the one sample of 58 sales. I'm given the mean of those sales. I'm given the standard deviation of those sales. And I also have a value that I want to compare my sample mean to, right? So the type here is one sample mean. So what I want to do, as soon as I've decided that I have a one sample mean question, then I'm going to focus on just this portion of that formula sheet that I posted, or some version of it, right? You're working open book and with your own papers and your own stuff, right? And so if you have the equivalent of this, I just gave you this so that you would have a guide, right? But that means, whoops, that you're going to be looking in this section. And once you've decided what type of question you have, right, then you really zero in on that. There's no point in jumping around on your formula sheet anymore, because this is the type of question that you have decided that you have, right? So that's why it's going to help you a lot if you just start by really convincing yourself what type of question you have, because that lets you zero in on your formula sheet, or kind of maybe you have some different one-pagers, or maybe you have some summary sheet for each type of question. And then you can pull that out and say, okay, this is how I do a hypothesis test, and this is how I do a confidence interval for this type of question, right? So that's going to be kind of your first thing. It can be really hard, right? If you're given a series of different questions, then maybe it's really difficult to decide what type of question you have, right? So that's going to probably require the most work, right? Everything else just kind of runs on rails. And what are we given here? We're given, in the order that it appears, right? All the information that I've been given is that before the redesign, and it's not obvious, right? But the average sales were $24.85. And if we read on, then we realize that this is the value I want to compare my sample mean to, right? And so that means that mu naught is $24.85. And I drop the units. You can insert the units later, but usually we just drop the units because they should be the same. It shouldn't matter. Okay. So then the value we want to compare our sample mean to is $24.85. Oops. After the redesign, they select a sample size of 58. What's the 2000? The 2000 is a decoy. And that's going to happen, right? It's not a decoy necessarily. It's the population size, right? But n, lowercase n, is our sample size. So n is 58. Capital N is the population size, but it doesn't play a role in any of our calculations, so we can ignore it, right? And the sample mean, X bar, is 2605, and the standard deviation, S, is 1020. And then here, if we want to know if the sales have increased, that makes it a one-sided test, right? So a one-sided test, which will reflect in our alternative hypothesis. Okay. We're also going to build a confidence interval, and we can build a 95% confidence interval as well, but I'll follow that up once we finish this big question. Okay, so step one is to state the hypotheses. Okay. So we start the same way that we have been doing H naught and HA, and these are statements, right? My null hypothesis is this, my alternative hypothesis is this. And from the formula sheet, right, if we need a crutch, then we know as soon as we're talking about a mean, then our hypothesis has to be about the population mean mu, Okay, so you're always hypothesizing about the population. You're not hypothesizing about what the sample looks like. You know exactly what the sample looks like. Okay. So then our hypothesis is that mu, and we've already identified mu naught as 2485, right? So mu is 2485. What we want to know is there evidence the mean sales have increased since the redesign, right? So is the mean now larger, significantly larger, right, than 2485? Whatever we have here, we have to talk about in both hypotheses, and whatever the null value is has to be the same for both hypotheses, right? And so once you've decided your null hypothesis, the only thing that changes is the sign, right? Everything else stays the same. So then here, because I'm only concerned with an increase, that makes it a one-sided test. Right? I don't just want to know if there was a change since the redesign. I specifically want to know if there's been an increase. No? But that's our step one, complete, done. All right. So then step two is do the test. I usually put in kind of quotes because it's a weird way of saying it, but it's okay. Doing the test really means calculate the test statistic that is given on your formula sheet, right? If you can't remember what it is, then it's here, but it's going to be T is equal to X bar minus mu naught, right? How far is my sample mean of 26 something from 2485? Taking into account S over root N, which is the spread of X bar. So I want you to get in the habit of writing out your empty formula that you're filling in before you fill it in, because otherwise it's really hard to follow if you go back and you look at your work, right? Sometimes I get lazy and I don't do that, but most of the time I'm pretty good. 2605, how far is it from 2485? I think 2485. And my standard deviation was 1020 divided by a square root of 58. Yeah. So it's really important that you do the denominator first, right? 10.2 divided by the square root of 50. And let me grab my calculator. Sorry, 58. I said 50. 10.2 divided by the square root of 58. And I'm going to just show these middle steps here. 2605. I'm going to store this here. Okay. 2605 minus 2485 is 1.2 divided by, recall, 1.33932565. Of course, you're going to store all your decimal places or keep them somehow, right? But 1.2, oops, 1.2, getting sloppy here, divided by that guy. I get a T of approximately 0.8959733066. I have to round T to three decimal places to match the table, right? And so T is roughly 0.896, right, to 3 decimal places. Okay, good. I'm being picky, right? I'm using the approximately equal to. In fact, the approximately equal should have happened here because this is not the entire value, right? So as soon as you've got decimal places, you're approximating, but that's just me being mathematically picky. You can keep the equal sign all the way throughout if you want to. All right, so now I've got my calculated t, right? So here, this is our calculated t, which we can denote by t calc, right? I just find that it's a little bit easier to write that way, but it's your calculated t, and that's the one that we use in our table. But to use our t table, so step 3, find the p-value. And ideally, I want you to write out exactly what you're doing, right? Tell me everything that you're doing, or tell the reader everything that you're doing. So using the t table, so when I say using the t table, right, that lets me know that, okay, yeah, of course, I use the t table and that is the right thing to do because I calculated a t, right? So you're just highlighting everything that you do. With degrees of freedom equal to n minus 1, which is 58 minus 1, which is 57. But remember from last day, there is no 57 degrees of freedom on our table. Now there are different tables that we could use. Let's see here. And I think I'm going to just grab a chunk here, bring it in. I was ready for a, oh, didn't do enough there. Copy, I'll just clean this up so that we can make a copy of it. Okay. Copy, all right. Delete, delete, paste. All right. And I'm going to put a copy of that down here so that I don't need to do that ever again. Well, if I can remember, right? All right. So I go to the table and I'm trying to find 57 degrees of freedom, but I don't have 57. It goes from 1, 2, 3, all the way down to 30, I think. And then it goes from 30 to 40, and then 40 to 50, 50 to 60, 60 to 80, right? So not even consistent jumps anymore, right? But we always round down. So then to highlight that I know, to show off that I know to do that, right? I would say, but using degrees of freedom equal to 50, but using degrees of freedom equal to 50. Okay. So then I can draw, or I can kind of highlight here that that's the degrees of freedom line that I'm working on. And so nothing else matters in the table, right? All those other sample sizes don't apply, right? So you can ignore everything except for the top and the bottom, and that's all you need, right? So then what we're gonna do is we're gonna try to place our calculated value somewhere along this line, right? And so we had a calculated value and it was positive, but if it was negative, we would have to drop the negative, right? So the calculated is 0.896. Okay. And so what we're going to say here, using the t table with 57 degrees of freedom, but using 50, and then I've got the table here so we can reference it, but our follow-up is we find And how we structure it, right, is we take the absolute value of the t, and I like to put a little subscript calculated there, which was 0.896, is somewhere between, and 0.896 is between 0.849 and 1.047, right? So I can highlight these two if I want, right? And so here it's between 0.849 and 1.047. So what happens for our p-value, right? This is where we need to remind ourselves if we have a one-sided or a two-sided test. So you can scroll back to the alternative hypothesis, which was way back here, right? I have a one-sided test because I'm only interested in a significant increase. Significant decrease would be bad, right? If I redesigned their website and they had a significant decrease in sales, I don't want to be able to say that even, right? And so I'm only interested in an increase. So I have a one-sided test, right? Which means I have a one-sided p-value. So then I'm down here and I focus on this line. And what I'm going to find is that these two values that wrap around my calculated value, right, they map to some one-sided p-value, right? And it's really important that you read from right to left. Okay? And so here, so I usually write so or therefore, or something fancy like that. The one-sided p-value, right, as soon as we know what it is between 0.15 and 0.20, right? Read from right to left, right? Because 0.15 is smaller than 0.2. So our one-sided p-value is somewhere between 0.15 and 0.2. But notice how that interval, right, it's all above 0.05. So even the lowest value, 0.15, is greater than 0.05. And I think we were asked to use a confidence level of, or a significance level. Well, that was the other question. I don't have an alpha here, but I know the default is 0.05, so I'm going to use that. All right, so I have a range for my p-values. So all of a sudden I'm ready to go here. And step 4, I'll put it on a new page here. Step 4 is my conclusion. First thing I'm going to do is I'm going to compare my p-value to the alpha level. So since my one-sided p-value is between, so here I'm just articulating and I'm just writing out exactly what's going on here, right? Is between 0.15 and 0.2, is between 0.15 and 0.20. It is not less than our assumed alpha level of 0.05, right? If you have an alpha level, you don't have to say that you're assuming it is that, it's just given. But you can use the exact same terminology if you want to. So it's not less than our assumed alpha level of 0.05. I guess I don't have a period there, just a comma. This is the first part of our conclusion, right? Comparing my p-value to the alpha level. So since my one-sided value is between 0.15 and 0.2, it's not less than our assumed alpha level of 0.05, which means we do not, right? Then the p-value is not low enough. We do not have enough evidence to reject H naught. Okay. That's your conclusion in terms of H naught, right? We do not have enough evidence to reject H naught. Final conclusion, the actual conclusion that we were paid to do is, what does that mean in terms of the sales after the redesign? It's not good, right? It's not what we wanted, right? We wanted to show, right? The question is there evidence the mean sales have increased since the redesign? No. There's no evidence that the mean sales have increased significantly since the redesign. You can always throw in a significantly if you want to kind of boost what you're saying. Therefore, there is no evidence of, and I completely forgot what I was going to say here. There is no evidence, oops. Okay. There's no evidence that the mean sales have increased significantly they did increase on average, but not significantly overall, right? There is no evidence that the mean sales have increased significantly since the redesign. All right, and that's the moneymaker. That's why we were paid to make to do this t-test, right? What were the conclusions? And with these last few minutes, I also want to build a confidence interval, right? And so the hypothesis test is going to tell us if there's been a significant increase or not, right? And we found no. But what is the range of the expected increase, right? It's going to include the previous amount, right? But we can also build construct a 95% confidence interval for the population mean sales after the redesign. All right. So we have our sample mean after the redesign, and now I can build an interval for the population mean sales after the redesign. So I have X bar plus minus some T star times S over root N. Now I need my T star for a 95% confidence interval. And let me see if I still have it there. Okay. I did. So again, right, using degrees of freedom equal to, right, and maybe I'll say the degrees of freedom, because that's what we need to be able to find T star. The degrees of freedom is 58 minus 1, which is 57. But using degrees of freedom equal to 50. Now, if this is part of the same question, so it's just another part, you've already shown how to find the degrees of freedom, so that's fine, you can ignore it, right? But let's pretend that we're covering all our bases here. So we've got 50 degrees of freedom here, and I want a 95% confidence interval, so then here, 95% is here. So then my T star is 2.009. So T star is 2.009. Notice that that's only slightly different from 1.96, right? But it's going to make a slight difference in our interval, right? We're getting it a little bit wider because we're estimating two things is the reason, right? We're estimating the mean, but also the standard deviation based on the sample. All the other information I have already from the question, right? So then my X bar plus minus T star times S over root N. Here we go. I got 26.05, I want to say. 10.2 over root 58. And if you've already done that calculation, you can just plug it in. 2.009 times 10.20 over root 58. Right, so I've actually saved this value, the standard error in my calculator. So I can just go ahead and find that value, which was 1.33 something, times 2.009. So my margin of error is 2.69070561, 2605. What's nice about money is we know that we round to 2 decimal places, right? And so money or dollars round to 2 decimal places. So we can go straight to 26.05 plus minus 269. Make sure you round properly here, right? Then I get an interval of 2605 minus 269 is 23.36 up to 2605 plus 269, 28.74. We have to interpret this interval, and I know I'm just zooming through here, but we are 95% confident the interval, and here is where I'm going to insert the dollar signs, right? So we're 95% confident the interval from $23.36 to $28.74 captures the population mean, right? So we're always trying to capture the population mean or proportion. And I'm going to refer back to the question that I made up. So I want to make a 95% confidence interval for the population mean sales after the redesign. So then captures the population mean sales after the redesign. We did it. Okay. So that's a hypothesis test and a confidence interval for one sample means questions. I think you'll be pleasantly surprised when you see the paired problems. So if you have 2 samples, but they are paired, naturally paired, then we basically just reduce it to a one sample means question again, right? So that's for tomorrow, but really great job. And if you have any questions, let me know. Otherwise, we'll see you next week. Thanks, guys. Stop this.